Alright, this is day 2, section 2.3, momentum and impulse. Newton's third law of motion says if body A exerts a force on body B, then body B will exert an equal and opposite force on body A. And that's shown here in this picture. We have the man pushing against the car, so he's exerting force F on the car in the right direction. But Newton's third law says the car is also exerting a force in the opposite direction with the same magnitude, negative F. These forces don't balance each other in a free body diagram because they're on different objects. Remember, when we do a free body diagram, we say something is in equilibrium, we're talking about one object. So if we're talking about the car, for example, this negative F is being produced by the car. So that isn't listed on the free body diagram. What's happening to the car is the man pushing on it. So if we're going to do a free body diagram of just the car, we would have just this force listed on it. Equally, if we were to do a free body diagram of the man, what's happening to the man is the car is pushing on him with a force in this direction, negative F. But the forward force would have no bearing on his free body diagram. We're going to do a few examples from page 67 and 68 from your book. Example 1 from page 67 says, a body falls freely towards the ground, as shown in this figure from our book. They have the ground and a body falling down with the force of weight acting on it. According to Newton's third law, what else is happening? Well, Newton's third law says for every force, there is an equal and opposite force. There's a force that's equal magnitude, but in the opposite direction. So if we zoom out, we've got this ball falling towards the earth. If there is a force being pulled down, if there's a force acting on the ball due to the earth, there's actually also a force acting on the earth due to the ball in the opposite direction. That's what Newton's third law says. And again, it acts from the center of the body. Weight acts from the center of the body. Example 2 from page 67 says if we have a box sitting on the floor, there are two forces acting on the box. The weight of the box is acting down from its center, and there's a normal force acting from the ground it's sitting on, acting up on the box. According to Newton's third law, what is also true? What's also true is there are forces acting on the ground or the earth. There's a force of weight acting up from the center of the earth, and there's also a force acting down from the box. And these magnitudes are equal and opposite because the box is not moving. Example 3 from page 68 doesn't have any math, doesn't have any figures. It just makes use of, again, Newton's third law when firing a gun. It says the first law implies that if the bullet travels, if it changes velocity, there has to be an unbalanced force acting on it. So if we have the bullet coming out of a gun, there was a force acting on the bullet that's coming from the gun. Well, what it states then is there has to be an equal and opposite force from the bullet having acted on the gun. And that's what's called recoil. When you fire a gun and it kicks back in your hand, it's because of this equal and opposite force of the bullet pushing back from the gun. However, because the mass of the bullet is much less than the mass of the gun, the velocity of the bullet is faster than the velocity of the gun. And that has to do with conservation of momentum. Example 4 from page 68 is also, it's not a word problem, it's just explaining a concept. It talks about using a water cannon to disperse a crowd. If you shoot a water cannon at a wall, the wall stops the water. Therefore, the wall is acting on the water because there's a change of velocity. However, according to Newton's third law, there's also a force of the water acting on the wall then. And the same thing's true with demonstrators. If you have somebody demonstrating and you shoot a water cannon at them, they're going to stop the water. So there's a force that the people are enacting on the water. However, there's an equal and opposite force of the water pushing against the people. Momentum and collisions. Here we have a system, a before, a during, and an after. Initially, we have two balls of different masses, mass 1 and mass 2, traveling at two initial velocities that are also different, u1 and u2. They collide, and afterwards, the balls have the same mass, but they have different final velocities. Different from each other and different from their initial velocities. Using two of Newton's laws of motion, number 3, which says, during a collision, the forces acting on each ball are equal and opposite. So we can say this equation, F1 equals negative F2. And then because of Newton's second law of motion, we can say that the force is equal to the change in momentum divided by the change in time. The change in momentum being the momentum afterwards minus the momentum initially divided by the change in time. And that's true for both balls. We can combine these these three equations into one very, very big equation. That says the mass of one times the velocity of one, the initial velocity, plus the mass of the second ball times its initial velocity is equal to the mass of the first one times its final velocity, plus the mass of the second one times its final velocity. That is the momentum initially of these two added together equal the momentum of these two added together at the end. This is the law of conservation of momentum. We're going to do a few more examples from page 6970, where the collision where two bodies are joined together and an explosion. This is going to be problem 1 from page 69 in your book. It makes note that these have to be isolated systems where there are no other forces acting on them, just what is given in the problem. We have two balls, one that's 100 grams and one that's 500 grams. The second ball is at rest and the first ball is traveling at 6 meters per second. Then afterwards, after they collide, the two balls are joined together and they're traveling at a equal velocity. What is this velocity of traveling with at the end? Well, we can use Newton's law of conservation of momentum that says the initial momentum of the two masses added together, U for initial, is equal to the final momentum. Now notice I didn't put a V1 here and a V2 here because they're traveling at the same final velocity. I want to remember that that's the same velocity. Mass 1 is equal to 100 grams times 6 meters per second plus mass 2 is 500 grams times 0 meters per second because it's not moving. That is equal to, and I can reorder this, the velocity times mass 1 plus mass 2. Mass 1 plus mass 2 is equal to 600 grams. (100 times 6 is 600 gram meters per second. Divide both of these by 600 grams. And I'm left with V is equal to 1 meter per second. This is example 2 from page 70 of your book. Yes, page 70. So we have a ball. Actually, it says a mass of clay weighing 120 grams that's just sitting there. So it has no velocity. And it explodes such that a 20-gram chunk flies in this direction with a velocity of V, and a 100-gram chunk flies in the other direction with a velocity of 5 meters per second. What is the velocity of the 20-gram piece? And again, we use the law of conservation of momentum. All right, so the initial is the total mass. So I just call that m times the initial velocity. The 1's not necessary because there's only one mass. Is equal to the mass of 1 times its velocity. Actually, its velocity is in the negative direction, so I need to put a negative sign here. Plus the mass of the second one times its velocity. And its velocity is in the positive direction. So again, I'm going to call this positive and this negative. So I have a negative sign here and a positive sign here. The momentum here is 0. 120 grams times 0 is 0. So 0 is equal to negative, the mass of 1 is 20 grams, times the velocity we want to find, plus the mass of 2 is 100 grams, times 5 meters per second. I'll go ahead and move this to the other side. So I have 20 grams times V is equal to I'll just do the math, 500 grams times meters per second. Now it's important to note I'm leaving grams here. Momentum needs to be used when we calculate momentum, the units have to be kilograms. But we don't have to convert to kilograms because we're going to be canceling those out and we're searching for V. So as long as these units are the same, we don't have to convert to kilograms first. As you can see, the units will cancel out. Divide both sides by 20 grams. Grams cancel out. And you get V is equal to 500 divided by 20, which is 25. These are some real-life applications on how we use conservation of momentum. And they're very similar examples, a rocket engine and a jet engine. Here's a diagram of a rocket engine. Before we burn the fuel that's inside of it, there's no momentum. And when we start burning the fuel, what happens is the momentum of the gas shoots out. But in order to conserve momentum, to have a net of 0, this momentum of gas is offset by the momentum of the rocket. So we have an equal and opposite momentum. And the idea for the jet is similar, except instead of starting at 0 and going to some velocity for the gas, so here we have no motion whatsoever for the rocket. For a jet engine, we're taking air moving at some velocity and increasing the velocity. And so when we increase the velocity of the air, we're also increasing its momentum. So the momentum of the air coming out of the jet has to be offset by the momentum of the jet or the plane itself being propelled forward.